Hello everyone, in this video we are going to discuss the theory linear programming and matrix form. In this discussion we are only going to focus on its theory, and in the next video we are going to continue the topic and give some examples for better understanding. What is linear programming? Linear programming is a method of optimizing operation with some constraints. The main objective of linear programming is to maximize or minimize the numerical value. Linear programming is considered an important technique that is used to find the optimum resource utilization. The term linear programming consists of two words as linear and programming. The word linear defines the relationship between multiple variables with degree 1, and the word programming defines the process of selecting the best solutions from various alternatives. The theory of linear programming provides a good introduction to the study of constraint maximization and minimization problems where some or all the constraints are in the form of inequalities rather than equalities. Many models in economics can be expressed as inequality constraint optimization problems. A linear program is a special case of this general class of problems where both the objective function and the constraint functions are linear in the decision variables. Linear programming was developed by George B. Dantzig in 1947, which is as a technique for planning the diversified activities of the U.S. Air Force. In the year 1958, Dorfman, Samuelson, and Solow go on to note that Dantzig's fundamental paper was circulated privately for several years and finally published as Dantzig. Linear programs appear in many economic contexts, but exact form of the problems varies from across application. Linear programming is widely used in mathematics and some other fields such as economics, business, telecommunication, and manufacturing fields. And in this video, we are going to discuss the definition of linear programming, the theory linear programming and matrix variable, and the simplex method and its revised simplex methods to solve linear programming problems.
So there are three types: the non-homogeneous Farkas theorem for matrix spaces, number 2, linear programming for matrix variables, and number 3, complex and quaternion linear programming. So linear programming is formulated with the vector variable replaced by a matrix variable with the inner product defined using trace of matrix. The theorems of Mott and N. Farkas, both homogeneous and inhomogeneous forms, and linear programming duality thus extend to matrix variables. Duality theorems for linear programming over complex spaces and over quaternion spaces follow as special cases.
Linear programming for matrix variables. We first introduced matrix concepts in linear programming by developing a variation of the simplex method called the revised simplex method. This algorithm, which has become the basis of all commercial computer codes for linear programming, simply recognizes that much of the information calculated by the simplex method at each iteration. Thus, efficiencies can be gained by computing only what is absolutely required. Since matrices are basically a notational convenience, this reformulation provides essentially nothing new to the simplex method, the sensitivity analysis or the duality theory. However, the economy of the matrix notation provides added insight by streamlining the previous material and in the process highlighting the fundamental ideas. Further, the notational convenience is such that extending some of the results of the previous chapters becomes more straightforward. The revised simplex method, or the simplex method with multipliers, as it is often referred to, its modification of the simplex method that significantly reduces the total number of calculations that must be performed at each iteration of the algorithm. Essentially, the revised simplex method, rather than updating the entire table at each iteration, computes only those coefficients that are needed to identify the pivot element. Clearly, the reduced cost must be determined so that the entering variable can be chosen. However, the variable that leaves the basis is determined by the minimum ratio rule, so that only the updated coefficients of the entering variable and the current right-hand side values are needed for this purpose. The revised simplex method then keeps track of only enough information to compute the reduced cost and the minimum ratio rule at each iteration.
In 1947, George B. Danzig developed a technique to solve linear programs. This technique is referred to as simplex method. So, the simplex method is an approach to solving linear programming models by hand using slack variables, W's, and pivot variables as a means to finding the optimal solution of an optimization problem. So, at each iteration of the simplex method, only the column corresponding to the variable entering the basis needs to be computed. So, a linear program is a method of achieving the best outcome given a maximum or minimum equation with linear constraints. So, most linear programs can be solved using an online solver such as MATLAB, but the simplex method is a technique for solving linear programs by hand. To solve a linear programming model using the simplex method, there are steps that are necessary.
Revise simplex method. Step 0. An initial basis inverse b with a negative 1 is given with segment b equals to b with the exponent of negative 1 b greater equal to 0. The columns of b are a, j1, aj2, etc. ajm, and y is equal to c with the exponent of b. b with the exponent of negative 1 is the vector of simplex multipliers. Step 1. The coefficient of segment C for the non-basic variable xj are computed by pricing out the original data aj, that is, segment cj and cj minus yaj equals to cj minus the sum of m I equals to 1 yiaij for j non-basic. If all segments cj is less than equal to 0, then stop. We are optimal. If we continue, then there exists some segments cj greater than 0. Step 2. Choose the variable to introduce into the basis by segment cs equals to maximize braces segment cj parallel segment cj greater than 0. Compute segment as equals to b with the exponent of negative 1 as. If segment as less than greater 0, then stop. The problem is unbound. If we continue, there exists segment is greater than 0 for some I equals to 1, 2, etc. m. Step 3. Choose the variable to drop from the basis by minimum ratio rule. The minimum ratio rule is segment BR over segment ARS equals to minimum brace segment BI over segment AIS bracket segment AIS greater than 0. The variable basic in row R is replaced by variable S, giving the new basis B equals to bracket AJI etc. AJR minus 1 AS AJR plus 1 etc. AJM. And for the step 4, determine the new basis inverse B with the exponent of 1, the new right hand side vector segment B, and the new vector of simplex multipliers is y equals to c with the exponent of b, b with the exponent of negative 1 by providing an segment ARS. For that step 5, go to the step 1 again. We should remark that the initial basis in step 0 usually is composed of slacks variables and artificial variables constituting an identity matrix, so that the p equals to I and b with the exponent of negative 1 equals to I also. The more general statement of the algorithm is given since after a problem has been solved once, a good starting feasible basis is generally known. and it is therefore unnecessary to start with the identity basis. And for the example and continuation of this will be in the next video. Thank you.